We are living in a world where the demand for energy is increasing rapidly. Having prospects of a transportation system based on electric vehicles, we need to find systems how to produce more energy in a sustainable way while reducing or better eliminating greenhouse gases and pollution. Renewable energy resources are very important, but generally they produce intermittent energy and use expensive equipment prone to weather exposure. Can we produce enough energy in a more sustainable way? Both fossil fuels and most of our renewable energy is a result of the energy produced by our star, the Sun. So why don't we produce energy as the Sun does? Light and heat energy produced by the Sun is the result of a fusion reaction. In the Sun's core, hydrogen nuclei fuse together to form heavier helium atoms. If we compare the mass of the nuclei we started with to the mass of the products, we find that this is different. There is a mass defect. But the mass cannot just disappear. According to Einstein's famous equation, E is equal to mc squared, energy is equivalent to mass. So fast-moving nuclei have a larger relativistic mass. In fact, the mass defect accounts to the large kinetic energy that the fusion products possess. The energy produced in fusion is much larger when compared to the energy produced by burning fossil fuels, or the energy produced in fission reactions when atoms are split up. The problem when fusing two positive nuclei is that these exert repulsive electrostatic forces on each other. In the Sun, the pressure in the core, resulting from the very large gravitational forces, managed to overcome these electrostatic forces, such that fusion can occur at a temperature of 15 million degrees Celsius at its core. On Earth, we cannot reproduce the conditions as inside our Sun, so we can start fusion only if the temperature of the nuclei is about 150 million degrees Celsius, 10 times higher than the hydrogen fusion reaction in the Sun. Humans actually managed to produce the very first hydrogen fusion reaction on the 1st of November 1952, when the first thermonuclear bomb named Ivy Mike was detonated. The temperature was increased by first detonating a fission atomic bomb, and this then started the hydrogen fusion reaction. This bomb produced an explosive power 700 times that of the fission bomb dropped on Hiroshima, destroying the whole island on which it exploded. The largest obvious problem in producing a controlled fusion is how to increase the temperature of the nuclei to a staggering 150 million degrees Celsius in a closed environment. If we manage to do so, there is no material in the world which can keep contained this hot plasma. So, we need to heat the nuclei and at the same time keep them from touching the walls of the container. How can we do this? The answer is by using a donut. Well, a donut-shaped container called a tokamak. The fusion fuel that is used in a tokamak is hydrogen. Actually, two different isotopes of hydrogen can be used for fusion. Deuterium hydrogen has one proton and one neutron in its nucleus, while tritium hydrogen has one proton and two neutrons in its nucleus. These hydrogen atoms are accelerated and stripped of their electrons, producing a plasma made up of positive nuclei and negative electrons. These positive and negative ions are introduced in the tokamak, and this vessel is surrounded with very powerful superconducting magnets kept at very low temperatures, close to absolute zero. Now, When a fast-moving ion enters a magnetic field, it experiences a magnetic force, and thus it starts to move in a circle. So the magnetic field in the tokamak is such to shape and keep the plasma confined away from the walls. Besides this, the changing magnetic fields create a high-intensity electric current by induction through the plasma. The charged ions become energized and start colliding with each other. This starts to increase the temperature of the plasma. Other external heating methods using particle injections and electromagnetic waves increase the temperature of the plasma to 150 million degrees Celsius, and so fusion can start. When the deuterium and tritium nuclei fuse together, they produce a helium nucleus and a very fast-moving neutron. 80% of the energy is possessed by the neutron, which is not affected by the magnetic field around the tokamak, and therefore it moves out of the magnetic confinement to be absorbed by the walls of the tokamak. Water flowing behind the walls pick up this heat energy. This system can further heat water in a boiler producing steam, which finally turns turbines to produce electricity using generators. The first fusion experiments date back to the 1930s, but the most successful was the joint European Torus experiment in the UK, which achieved the world's first controlled fusion power in 1991. Today, in southern France, a new fusion test reactor is being built, with the aim to create a stable fusion reaction and producing more power from fusion than consuming power by the heating systems. They are targeting of producing 500 megawatts of fusion power for 50 megawatts consumed. This project is called ITER, International Thermonuclear Experimental Reactor, and is the result of an international cooperation between various countries in the world. This will be the largest fusion reactor ever built, measuring 30 meters in diameter and 30 meters in height. The tokamak will be made up of 9 vacuum vessel segments, where the plasma is going to be contained at 150 million degrees Celsius, having diverters at the bottom to collect the helium and other impurities. These vessels are lined with 440 blanket modules, which besides absorbing the neutrons' energy, will also contain lithium to produce tritium to be used as fusion fuel. The vessels are surrounded at the top and bottom with 6 circular palladial magnets and 18 toroidal D-shaped magnets around the torus to confine the plasma inside and away from the walls of the vessel chamber. In the middle, a central solenoid helps to build this magnetic confinement and twists the magnetic field lines to induce the electric current in the plasma to heat it up. Everything is enclosed in the cryostat, which is a large stainless steel high vacuum pressure chamber to provide an ultra-cool environment for the ITER vacuum vessel and the superconducting magnets surrounding it. Fusion energy releases 4 million times more energy than burning fossil fuels and 4 times as much as the present nuclear fission reactors. The fuel used for fusion is extracted from water, so this ensures energy production for thousands of years. No greenhouse gases are produced, and the only byproduct is helium, which is inert and non-toxic. However, the high energetic collisions inside the tokamak make the materials radioactive, but they have no high activity or long-lived, in contrast with the present fission nuclear power stations, which produce highly radioactive waste which can also be used for nuclear weapons. Finally, there is no risk of meltdown, as if anything happens, the plasma cools down immediately, stopping fusion. Fusion energy, together with renewable energy resources, may actually be the key to have enough sustainable and clean energy for our future.